In this video, we're going to discuss how electrons are arranged within an atom. You know from GCSE that electrons are arranged in shells, and you were told that there were 2 electrons in the first shell, 8 in the second shell, 8 in the third shell. What we're going to explain now is, in actual fact, the first shell contains 2 electrons, the second shell 8 electrons, the third shell can hold up to 18 electrons, and the fourth shell up to 32 electrons. I'm going to explain why. So here on this diagram we have got the different shells labelled as 1, 2, 3, 4. The official name is actually the principal quantum number, but we don't need to worry about that from the perspective of A-level students. This arrow signifies that the shells are increasing in energy and are further from the nucleus. Now, the other striking thing about this diagram is that the shells are split up into these different sections here, which we call subshells. Now, the confusing aspect initially is that there is no consistency in the subshells between the between the different energy levels. And so what you can clearly see here is that in the first shell there is only one subshell, and we call that S. In the second shell there is an S subshell again, but now there's a P subshell. In the third shell there is an S, a P, as before, but now there's a D subshell. And also the fourth shell contains the S, P and D, and now contains the F subshell. So these different subshells gives us a clue as to why we have different numbers of electrons in the different shells. Also, what this diagram shows is that the subshells within an energy level, or within a shell, are themselves of different energies, and that becomes important very soon. Okay, now, you don't have to be able to regurgitate these, but you need to apply these principles. Now, how the electrons are arranged in atoms. Heisenberg's uncertainty principle. You may have heard of Heisenberg from Breaking Bad. And the reason for this, why the character was called this, is that Heisenberg uncertainty principle is you cannot determine both the position and momentum of an electron at the same time. So basically, you may know where an electron is, but you don't know where it's going to go to next. Pauli's exclusion principle. No 2 electrons can have the same 4 quantum numbers, which means that what we will say is that they have opposite spin. The Aufbau principle, electrons enter the lowest energy level available, and Hund's rule of maximum multiplicity. When in orbitals of equal energy, electrons will try and remain unpaired. Okay, and to me that's the sitting on the bus rule. Okay, so the electrons, we've talked about them being in the shells. The shells are divided into the subshells. The subshells are divided into orbitals. Now, what is an orbital? An orbital is a volume of space, or a region in space, where you can find where there is a 95% probability finding the electron. Orbitals can be empty, or they can hold 1 electron or 2 electrons. But if they've got 2 electrons, they must have opposite spin. And that becomes important when we look at the box diagrams in a few moments. The orbitals have different shapes depending upon which subshell they're in as well. Okay, so the shapes. So the S orbital is spherical. That's easy to remember. S, spherical. The P subshell is divided into 3 orbitals. And each orbital can contain 2 electrons. So that means the P subshell can hold 6 electrons. These are said to be called dumbbell shaped, although funny looking dumbbell to me. But you need all 3 p orbitals to make a p subshell. The d orbitals, there are 5 of them now, and these are quite strange in shape. There is some double dumbbell, and then there's the dumbbell with the collar. Again, you don't need to know the names, you don't need to know where the relative positions are. You just need to know that there are 5 orbitals in the D subshell. And then in the F subshell, there's actually 7 orbitals, but their shapes are very, very peculiar. Now, the reason the reason these orbitals are of a peculiar shape, it's not that we've designed them, it is statistical mapping of the probability of finding those electrons. Okay. So the order of filling the orbitals. So ultimately what we want to do now is to be able to write the electron configuration in terms of the shell, or the energy level, the subshell, and how many electrons are in each subshell. Okay, so first of all we'll set out our subshells, and as I said before, the higher the subshell, the further away from the nucleus it is. Now, you always fill the orbitals in the lowest available energy level, and then you add the electrons in to the next lowest energy level available. Okay. Now, as you get further away from the nucleus, the quantum shells get closer together, and you do start to get some overlap in the energy of the subshells. Okay, so the first time this occurs, and this is the time that we need to know, is that in actual fact the 4s orbital is filled with before the 3d orbital because it is at a lower energy. Okay, so the 4s orbital is still part of the 4th shell, and it's physically further away from the nucleus, but it's lower in energy, so that's why it's filled first. So in actual fact, what we'll do is we will change our order so that we will fill our subshells in the order of 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 4d, 4f. Now, how do you know how to remember this? There are a couple of ways. The first way is the arrow method. Okay, you'll see this kind of template in your booklets, and you've got here the S subshells lined up below each other. The same for the P, same for the D, same for the F. Okay. If you draw a series of parallel arrows going through the orbitals like this, then what you'll see is that you fill, first of all, the 1s subshell. Then you will fill the 2s subshell. Then you fill the 2p, then the 3s. This is followed by the 3p and the 4s. And then you go to the 3D, the 4p, the 5s, then the 4D, 5p, 6s, and then finally we get to the F subshells, or the F orbitals, to the 5D, to the 6p, to the 7s. Okay. So it's really important that you remember that the 4s orbital is filled before the 3D. Okay. So we're going to look at some of the elements here. So I'm just going to look at a few. So we said before that the electrons must have opposite spin. Okay, so our definition of an orbital is a region or a volume of space which can occupy two electrons with opposite spin. Okay, so here we color-coded our s orbitals, our p orbitals, and our d orbitals. Okay, so the first element, hydrogen. So we put our first electron in the lowest energy level. Okay, so we put it in the 1s subshell or in an orbital in the 1s. Okay, so therefore hydrogen has the electron configuration of 1s1. Principal quantum number, the subshell, and the number of electrons in there. Okay. Helium. Now helium's second electron goes into the lowest available energy level, which is still the first energy level, but it must have, so it must, when it's in this orbital here, it must have opposite spin. So that should Pauli's exclusion principle. Okay, so the electron configuration for helium is written as 1s2. If we go to lithium now. Now, lithium has got 3 electrons, and in the past you would have wrote it as 2.1. Now we can say that there are 2 electrons in the 1s subshell, or in the 1s orbital. Now we need to go to the second energy level to put in the next electron. Okay, and that will go into a 2s subshell or a 2s orbital. So therefore, the electron configuration for lithium is 1s2, 2s1. Beryllium follows the same pattern, and it has the electron configuration 1s2, 2s2. Boron now. It's got 1 electron. It's boron now. It's got 5 electrons. 4 electrons are in the 1s and 2s. The 5th electron has to go into the 2p orbital, because that is the lowest energy orbital or energy level available. Now, it becomes more interesting now when we move along to carbon. Now, carbon goes into the carbon's 6th electron actually goes into the next available empty orbital. It doesn't pair up here with that previous electron, and that's due to Hund's rule of maximum multiplicity. The way I think about it is that if you get on a bus, there's one person sat on the row, you don't go and sit next to that person, you go and sit on an empty seat. Okay. Nitrogen, it's the 7th electron of nitrogen goes into the next orbital. Okay, and then when we get to oxygen, that electron now has to pair up. There's no way, there's no other place for it to go, but it must occupy the lowest energy subshell. Okay, so the electron configuration of oxygen is 1s2, 2s2, 2p4. Okay, and I need to leave it at that because I've run out of time.